All right, so this is a quick review of the forces section. A couple of quick things to note before we start getting into the equations. In general, when dealing with forces, essentially what you always want to start with is a free body diagram. So your step one of any one of these problems should be a free body diagram. And so you want to make sure to set up your axes, have an X and Y direction, put just your object at the center, and then start drawing in whatever forces you have. Normal force going directly upwards, maybe a force from gravity going directly downwards. Any forces in your X direction. Sometimes we have something like a tension force, maybe an opposing force from kinetic friction. Those sorts of things. Always start with setting up your free body diagram. The next step that you want to take is the sum of the forces in the X direction and the sum of the forces in the Y direction. So in this case here, we would have the magnitude of Ft cosine theta in the positive X direction minus the magnitude of Fk in the negative direction. And we have in our positive Y direction Fn, we also have the other component of the tension force that I drew in. And then in the negative direction, we have the force from gravity. Always start like this. That will allow you to sort of lay everything out. Step 3 then is to include the motion. So this is where you use Newton's second law over here, F net equals ma. So you have the sum of the forces in the X direction is equal to the mass times the acceleration in the X direction. And you want to be careful, is this positive or negative? And then similarly, your sum of the forces in the Y direction is equal to the mass times the acceleration in the Y direction. And you want to be careful, is that positive or negative? And so basically you take your equations that you set up from part 2 and then set them equal to the motion. And then you can start plugging things in and working through what the problems are. And after you go through these 3 steps, step 1, step 2, step 3, really then you often end up with a mathematical manipulation. But make sure to go through those 3 steps first sort of methodically, and that'll stop you from making some simple mistakes. Once you have those things down, it's important to start thinking about what the various types of forces are. So one that comes up most often is when we're talking about weight. And so weight is just a mass times gravity. And when we say gravity there, we're talking about the gravitational constant. So the equation on your equation sheet gives you really the magnitude of the force from gravity, and that's equal to the mass of your object times the gravitational constant there, which we treat as 9.81 meters per second squared. So deal with your signs from your free body diagram. Don't deal with your signs from the force from gravity. The next equation has to do with Newton's third law, and we know with Newton's third law we have force pairs that are equal and opposite. So if you have 2 different objects, third law, if you have 2 different objects that are interacting some way, then you're going to have equal and opposite forces arising from those. So one block pushes on the other and they push on each other in different directions. The biggest tip that I'll give here is come up with 2 or even 3 free body diagrams, and the third one would be the combination of the 2 objects together. So that's an important thing there. Next, we deal with friction. When dealing with friction, you have 2 types of friction. One is static, and the other is kinetic. So basically, with static friction, we're talking about a threshold for motion. And so the static friction force, FFS, will grow as you pull on an object or as you try to move an object as static friction holds it there until you hit FFS max. And that is mu s times a normal force. And so in general, we have this less than or equal to thing here, and then we have a max condition that gives us motion. If your object is moving already, then you just use the kinetic friction. And for kinetic friction, that's where Fk is equal in magnitude to mu k times the magnitude of our normal force. An important thing with all these friction problems is that we have this normal force in there, and so often we're tying the vertical and horizontal components of net forces together. So that is going to be a problem where in our free body diagram here, you often will have to figure out what's going on in the vertical direction so that you can then plug it into what's going on in the horizontal direction with friction. The last two things that we deal with are drag and uniform circular motion. For drag really just comes down to this simple equation here. One thing to note for drag is that, so drag concepts that are important. One is terminal velocity. And terminal velocity, if your object is falling straight down, is going to be when your drag force is balanced by something like gravity. And so there, your quick and simple free body diagram would be gravity down and drag up, and that's the x and y direction. So gravity down and drag up, and your speed is going to increase until you get to a point where your drag force balances out the force from gravity. And then you have no additional acceleration, so your sum of your forces in the y direction would be the force from drag up and the force from gravity down, and that is equal to may. And if your speed is no longer increasing, then ay is 0, so you know your 1/2 c rho a speed squared is then equal to m times g. And you can solve things out from there, like what your actual terminal velocity is. So that would be your terminal velocity. All right, and then the last thing we have is uniform circular motion. And really, the idea with uniform circular motion is you're just tracking where your centripetal acceleration is. And so we know that our net force is equal to ma, and for uniform circular motion, that acceleration there is a centripetal acceleration. And so we can do all sorts of things here, like figure out what that acceleration is if we know something about our motion with v squared over r, and we can figure out v if we know the circumference of our circle divided by the time to get around it, or the period. So time there is in seconds. And so really this just comes down to carefully tracking what sort of free body diagrams you have in those sorts of things. In circular motion, you're often going to end up with a net force that is sort of seemingly unopposed in your free body diagram, and you just want to think about that force as the thing that keeps your object moving in a circle and stops your object from slipping towards the outside of your circle. And then we know that that centripetal acceleration is center seeking. So your net force should be pointing towards the center of whatever your circular motion is if you have uniform circular motion and thus centripetal acceleration. So that breaks down the forces section. We have Newton's laws. We have a bunch of different types of forces, and all of that lets us relate a net force that we find with our careful three-step free body diagram process to the motion of our objects and then track some interactions there. The biggest tip I have, again, is make sure to go through this three-step process and then separately look at what the math is to figure out whatever parameters you're missing.